So what's happening if we take our mass on the end of a spring and put it in a container that contains some sort of resistive medium? If I put this in a container full of oil or a container full of water, or if I attach the bottom to a piston, is this still 5 foot? Yep. Then the mass would drive the piston, right? And the compression would act as a resistive behavior. We get some sort of damping behavior. Which really depends on drag. Okay. I watched people in the physics lab past week, dropping coffee filters. They were looking at drag, air resistance, but that depends on velocity. So I'm going to end up with a force that points in the opposite direction of the direction of motion. But this time it's based on velocity. And that means I'm accelerating. And then I have the spring. And then I have this new thing where this beta, bigger than 0, is a damping constant. Like our spring, that's determined experimentally. We actually attach a weight to the piston or dash pot or resistive medium, and we measure how much it causes things to slow down. Okay, I divide by m. X double prime is minus k over mx minus beta over mx prime. Move it all to one side. X double prime plus beta over mx prime plus k over mx equals 0. Second order homogeneous constants. We gave this a name, the k over m thing. What did we call that on Friday? Okay. I'm going to do another crazy, we called it w squared because then I took the square root and that was the pieces for our cosine and sine. That was the complex number part that gave us the phase. I'm going to do the same idea here. Only this time, instead of using a square, I'm going to call this 2 lambda. I promise the 2 is there for a reason. The 2 is there to make my life easier when it comes to the quadratic formula. Which really means my second order differential equation looks like this. Great. Fabulous. Wonderful. What the? The corresponding auxiliary equation that goes with this, since these are all constants, is r squared plus 2 lambda r plus w squared equals 0. Do the quadratic formula for me. negative b plus or minus the square root of b squared minus 4, a is 1, c over 2a, but a is 1. Wait a second. 2 lambda's quantity squared is 4 lambda squared minus 4w squared. If I factor a 4 out of that under the radical and I pull it outside the radical, it becomes a 2, which cancels with the 2 on bottom, which makes this minus lambda plus or minus the square root of lambda squared minus w squared. That's why I have the 2 in there, to make my life easier here. The 2 allows me to make the expression for the roots a little bit nicer. Okay. It's quadratic. What's the possibilities when I do this quadratic formula? How many roots can I get? That's an algebra question. I'm going to get 2 roots, right? But it's either 2 different real roots, 1 repeated real root, or 2 complex roots, right? How do I know which it's going to be?
Square. Square both sides.
Yeah. I don't want to square both sides. I've already gotten r equals, right? This is all the way down to r equals. Yeah. And if the thing is positive inside, 2 different real numbers. Lambda plus this thing, lambda minus this thing. If this thing is positive, its square root is a real number. On the other hand,
Bigger, it'll be negative inside the square root. Be
it won't be a real number, it'd be complex. What's left? Which would be if that's equal to 0. Okay, hang on a second. If that's my R value, those go in the powers. So I get C1 e to the negative lambda plus this square root stuff t plus C2 e to the negative lambda minus this square root t. Please notice I'm adding or subtracting inside an exponent here. That means I can split those up, which means I can factor out an e to the negative lambda t. And you said this was where lambda was bigger than w, right? lambda squared minus w squared bigger than 0. Those are both positive numbers. Lambda is bigger than w. So there's more damping than there is desire to oscillate. Because that's what omega w was. It was our oscillatory frequency, and that's the only place it shows up is up here. This wins. No matter what's going on here, it's going to be multiplied by e to the negative something. What happens as t gets bigger and bigger and bigger to this term? It gets smaller. And this is less than e to the lambda, isn't it? Because lambda is bigger than w, lambda squared is bigger than w squared. That means this square root is smaller than lambda, because that would be the square root of lambda squared. And we took something away. If this is smaller, then this is going to be more powerful. As t goes off to infinity, the product of those two will be negative. This one's already negative. This goes to 0 no matter what. This goes to 0, and this is smaller. It's not big enough to blow it up. As time goes on, this goes to 0. No matter what I do. The damping effect is bigger than the push. We call this an overdamped system. And it looks like an office door. If you look in the administrative assistant's office, right, not across the hall, but the next one over, the office where Dr. Segan is, that door's got a box on the inside of the door. When you close, when you let go of the door, you open the door, you let go, what happens? It slows down. It doesn't swing past the door frame and come back, does it? It slows to a stop in the door frame. That's this system. As a matter of fact, graphically, it looks like this. The blue line here pushes us slow. It is possible if we have a particularly heavy object, or maybe it's got a full swing through, it might go through once, but then it's going to go to 0. That's it. You won't ever get one full period out of this. It won't go back past where it started. Won't even get back to where it started. You'll get an overdamped behavior. On the other hand, if we got a repeated root, r equals minus lambda. What's our solution look like? Oh, sorry, it's not y, it's x. X of t equals C1 times what? Come on, people. This is on the homework I gave back to you last time. It's a repeated root.
XE or TE.
So if I factor the e to the lambda t out, I have C1 plus C2t, the equation of a straight line. Again, as t goes to infinity, what happens here? Because this is only big O of t. This is big O of e to the t, and it's in the bottom. This is going to win every time. Again, we're going to have a damping situation where the damping wins. But it turns out that it's just it's a little more than this because this is exponential. This was a little bigger than this is in terms of its order, right? This is of a bigger order, e to the something t, than this is, big O of t. So this is overdamped. This is the Goldilocks one. This is called critically damped. We balanced the amount of damping exactly with the amount of push. Again, we'll see either a smooth descent to zero or one motion and then we're done. If you took that door and pulled it open and let it go as you were pulling it open, it would open a little bit further and then it would swing back to closed. That's this upper graph right here. What if it's complex? What if we have lambda squared minus w squared is negative? I get two complex roots. Oh boy. All right, wait a second. R is negative lambda plus or minus the square root of lambda squared minus w squared, but that's negative, right? So I'm going to rewrite this as negative lambda plus or minus I times the square root of w squared minus lambda squared. Because that would switch it to being positive under the square root, wouldn't it? If this one is negative, reverse the order and you get something that's positive. What's my solution look like? Yeah.
Negative lambda x, the square root of those lambda squared. Okay.
Again, I can factor the e to the lambda t out. C1 cosine, disgusting number t, plus C2 sine, disgusting number t. Now, what the hell's going on here? That piece, the stuff inside the parentheses, what's it doing? That's our oscillation, right? That's the spring bouncing back and forth. So what's that causing to happen? What's the effect of this piece? Aha. Remember Friday? I had the experimental setup right here. I pulled the spring, I let it go. What eventually happened? The oscillation got less and less and less over time because what we've got is a graph of e to the minus lambda t causing this to slowly get smaller. This is called an underdamped system. That's more realistic to account for things like air resistance. Yes.
Why does that? What's happening is cosine.
Here?
Yeah.
Well, that's exactly what we did when we switched to be the complex part, right?
Okay.
That's the number that goes with the cosine and sine. The fact that this is negative is what gives me the cosine and the sine. And that's because that's the
Yeah.
alpha plus I beta or something, A plus IB, whatever we called it last time. That's the piece for the complex part. By the way, these two trig functions have the same period, right? The same frequency. I could combine those. Remember, we had that thing last time that said we could write it as A cosine omega t plus delta. Remember this thing? Oop, doesn't help if you can't see it. And this involved using the cotangent being C1 over C2. And then if I use sine, it was the tangent being C1 over C2. There was a formula for this. But that's going to show what happens as our stuff slows down, right? That makes something in real life. Because as we look at this graph here, at the beginning, the amplitude is getting smaller, but the period really isn't noticeably shrinking. As this gets smaller, the x-intercepts get closer together as well. And that means if I use this number, that takes the frequency and changes it, doesn't it? And it changes it by the damping factor. That's usually referred to as the quasi-frequency or the quasi-period. And so we shrunk what's happening. We slowed things down. $64,000 question. Why should I give a flying? Damping can happen in lots of different ways. If I put a spring here hanging, then my mass is going to be operated by the spring and gravity. What if I put another spring on the bottom as well as on the top and attach it to the table? Well, then every time we bounce back up, the spring on the bottom wants to pull it down. And every time we bounce down, the spring on the top wants to pull it up. So I get two springs acting as dampers to each other. Consider the electrons in an atom. What holds them in place is the nuclear forces, the electromagnetic force between the nucleus and the electron itself, right? You can picture that force as a spring binding the electron to the nucleus. But it also binds in a solid that electron to the next nucleus over. So you can consider all of these atoms as connected to one another with the intramolecular forces that are little springs. What happens when I bounce one of these electrons or atoms, by shining light on it? It moves in two dimensions. So I not only have an x of t, I have a y of t. Two simultaneously oriented differential equations. Doesn't matter. Just think of one direction for the moment. What happens is that energy gets absorbed and then re-emitted and bounces to the next atom and the next atom and the next atom. And what you're seeing here is light being absorbed and re-emitted repeatedly as it moves through a material. That's going to take a little while, isn't it? it's going to slow down our frequency. That's going to change the frequency of the light. And it's going to cause it to bend. This is the 3 blue, 1 brown video on why refraction works. And it is based on nothing more than treating atoms like springs and weights. People, I would be blind as a damn bat if we couldn't bend light by changing the material it goes through. That's how lenses work. The reason they work this way is because I solved this differential equation. Useless. Never going to be able to do anything. I couldn't see. We wouldn't be able to do any of this. We've got a lens up there projecting through the camera. I've got another one capturing the image in the first place. The only reason any of this stuff works is because I can solve a differential equation. Questions? Well, but then that's reflection, not refraction, right? But the color absorption is refraction, because as we go through the material, it reflects back the light that's green and it eats the rest of the light, absorbing it in the material. It's also why there are shiny spots and dull spots, because some of the light passes and some of it doesn't. Some of it's absorbed and some isn't. Put a straw in a glass of water. The illusion of it being broken, right? It's not really broken, it's just bent because the light is coming out of the water into the air, into your eyes. Okay. I'm going to step it up a notch. We called the f of t that was on the other side of a second order differential equation. We called it the forcing function or the driving function. So let's consider a non-homogeneous equation. Now, I've already written this one with x double prime all alone, but it could be mx double prime plus beta x prime plus kx equals some other f of t. But this is a non-homogeneous differential equation. How do I solve something like this? If I want to solve this first equation here, this one with the capital F of t, what do I have to do first? Which is going to give me one of those 3 cases we were just looking at, right? And then I can either use variation of parameters or undetermined coefficients or something like that to deal with the F of t. I know how to do this. It's just a new setting. So let's do an actual example from the top. A mass weighing 16 pounds stretches a spring by 8/3 feet, so 2 2/3 feet. I then take that mass, take it from equilibrium, and I pull it down 2 feet and let it go. The subsequent motion takes place in a medium that offers damping. And I'm just going to go ahead and give you the damping coefficient. Of 1/2. So we can picture the spring hanging from a bar. We pull it down 2 feet, we let it go, it starts to vibrate. Air resistance, fluid, whatever it is, maybe it's attached to something. The damping constant is 1/2 foot per second, pound per foot per second. The bar that is holding the spring is attached to a motor that makes it go up and down. Where am I going to see an already vibrating object have something within it vibrate? I don't know. Who drove today? Car? Me on the seat in the car? One vibration inside another, right? Now I call it a driving force for a reason. So there's my driving function. I want to write the equation here that's in parentheses. I have beta. I have little f of t. I need m, and I need k. How do I get there from here? Force gravity is what I need, right? But force, mass times gravity, it's force, and that's weight. Weight is 16 pounds. Perfect. What's m? Great. And now I know a step further. Mass times gravity, weight, equals kx, right? Wait a minute. What's X?
8 thirds.
The 8/3 foot we distorted by hanging the spring. Which means K is, multiply that by 3/8. Perfect. Now I can create my equation. 1/2 x double prime plus 1/2 x prime plus 6x equals 10 cosine 3t. If I go back and I look at the top, you'll notice that capital F of t is what happens when I write it with x double prime all alone. I'm going to go ahead and do that. That means multiply by 2 everywhere. I think that's probably a little easier to solve. But now I need to solve the homogeneous one first, and then I need to deal with the cosine 3t part. So I need to start with x double prime plus x prime plus 12x equals 0 and solve that. All right, wait a minute. That's r squared plus r plus 12 equals 0. Oh, crap. Out comes the quadratic formula, because that doesn't factor. I'm evil. I like completing the square here. So I'm going to write r squared plus r equals negative 12. Half the middle term, half of 1 is 1/2. 1/2 squared is 1/4. So I get r plus 1/2 squared equals, common denominator will be 48 over 4. So negative 47 over 4. I'm going to get an ugly ass complex root. R equals negative 1/2 plus or minus square root of 47 over 2i. That's just gross. 48 over 2? It's okay. Wait a minute. That means my complementary solution is C1 e to the minus 1/2 t cosine root 47 over 2t plus C2 e to the minus 1/2 t sine root 47 over 2t. Before I can solve for C1 and C2, because I have initial conditions, right? Before I solve for those, I need to deal with the particular solution part. Now you have a choice. You could do variation of parameter. With the integral formulas and the Wronskians and all that fun. You could do undetermined coefficients, depending on the right-hand side. What's the right-hand side in this problem? Cosine. Cosines are acceptable to use undetermined coefficients. And because it's just number cosine, I don't have any extra t's, that's very few numbers to solve for. I think I'm going to do it that way. So I'm going to say we're going to use A cosine 3t and B sine 3t. And then I'll take the derivatives, first and seconds. Oh boy. And then I'll plug them back in, right? I didn't say anything about this problem being short. But we can do it. What's the first derivative? Yp prime. And Yp double prime?
Two, five, eight, seven.
Great. Now that goes in to the equation up at the top and is set equal to 20 cosine 3t. Second derivative plus first derivative plus 12 times the original equation equals 20 cosine 3t. Ready? All right, cosines. Let's just look at cosines for a minute. Here's a cosine, here's a cosine, here's a cosine. What is the coefficient for cosine of 3t on the left-hand side? Okay, but negative 9a and 12a is 3a plus 3b. Now look at the sine terms. What's the coefficient for the sine terms? And now I know 3a plus 3b should be equal to 20, and negative 3a plus 3b should be equal to 0, because there are no signs on the right-hand side. Add those equations, you get 6b equals 20. So b is 10 over 3. That means that 3b is 10. So minus 3a plus 10 is equal to 0. And that means that minus 3a equals minus 10. A equals 10 over 3 also. Yay! So I now have the particular solution, and I have the homogeneous solution. So I kept calling it y. I should call it x. X of t equals C1 e to the minus 1/2 t cosine square root 47 over 2t plus C2 e to the minus 1/2 t sine square root 47 over 2t plus 10/3. A went with cosine 3t plus 10/3 sine 3t. I have initial conditions. X of 0 equals 2, x prime of 0 equals 0. I can solve for C1 and C2. I'm the first guy to tell you the numbers suck. Square root of 47 over 2? Barf. But a question for you. What happens as t goes to infinity?
Yeah.
Except we don't just have damping in this case. We also have the external force, right? The driving force. And the driving force was that 10 cosine 3t, right? As t goes to infinity, the damping is going to cause this part to go away. But what about this part? It stays, doesn't it? And that frequency matches the frequency of the driving force. In the long run, the internal vibration is overridden by the external vibration. This is transient. Remember back in chapter 2 when we talked about things that go to zero as t goes off to infinity? As transient solutions? That's exactly what's happening. No matter what the value of C1 and C2 are, there's an e to the minus 1/2 t there. That's going to cause that to go to zero. This doesn't do that. That's called a steady state solution. Now, if we don't have damping, but we still have a periodic forcing function, then it's the difference in frequencies that's going to be important. Because if we don't have damping, we won't get that e to the whatever t. We're just going to get a cosine or a sine. That was what we were doing on Friday. There was no damping. It was just vibrating. If the two periods match, then the amplitudes add. And we're going to get a t cosine t and a t sine t. What happens as t goes to infinity then? They get bigger and bigger and bigger, which means our vibration gets bigger and bigger and bigger and bigger, and the bridge shakes itself apart. Galloping Gertie, the Tacoma Narrows Bridge. That's exactly what happened. The natural vibration matched the forcing function. And the bridge tore itself apart. That's what happens when you sing at a glass. If you hit the same note that the glass is already vibrating at, you put more energy into that, force more energy, the glass wants to vibrate bigger, boom. That's called resonance. And it's a matter of resonant frequencies. It's exactly these two numbers matching up. By the way, every bit of this not only works in mechanical systems, it works in electric systems the same way. Resonant behavior in electrical systems is what causes that lovely feedback noise on a speaker. On electrical systems, that's what causes overload discharges and short circuits. Forcing functions override an incorrect electrical system. I don't know where we would use that. Do you? Pacemaker does that to your heart. Useless. I'm never going to use it anywhere. Tomorrow is question and answer day. Wednesday is the homework being due. Friday is the test. I would tell you to go look at the review sheet on Canvas, but Canvas is still down. Hopefully Canvas will be up shortly. You'll be able to get at the review sheet. You'll be able to get at the list of questions for the homework. If you can't see it later this evening, I will email you the list so that you have the list of homework questions at the very least. I'll email it anyway then. Absolutely. I got a meeting for the next 2 hours, but I'll do it at 6 o'clock. I will see you all tomorrow. Have a wonderful rest of your day.